Welcome to this coding problem walkthrough. Today, we'll be solving the problem titled Find n unique integers sum up to 0. This is an interesting and insightful problem that challenges your understanding of array manipulation and mathematical reasoning. Let's dive in and explore the solution step by step. The goal of this problem is to find an array of integers where all the integers are unique, and their sum equals 0. You are given an integer input n, which specifies the number of integers that should be in the array. The challenge is to construct such an array where the sum of these integers is exactly 0. Let's look at the input-output format. The input is a single integer, n, which tells us how many unique integers we need. The output is an array containing exactly n integers, all of which are unique, and their sum must equal 0. For example, if n is 5, you could output an array like -7, -1, 1, 3, 4. This array contains 5 unique integers, and when you add them up, the result is 0. Now, consider why the output array satisfies the requirements. In the first example, the integers -7, -1, 1, 3, and 4 are all unique and add up to 0. Notice that there are many possible answers to this problem. For instance, 0, -2, 2, -3, 3 would also work because it follows the same rules. The array has 5 unique integers, and their sum is 0. In another example, if n is 3, an array like -1, 0, 1 works because it contains 3 unique integers, and their sum is -1 plus 0 plus 1 equals 0. Another valid solution for this case could be -2, 0, 2. This highlights that the problem allows for multiple correct answers as long as the conditions are met. For the case where n equals 1, the solution is straightforward. The only array that satisfies the requirements is 0. This is because we need the sum of the integers to be 0, and with only one integer, the only valid choice is 0 itself. This makes 0 the unique solution for this case. Additionally, the problem comes with constraints to guide your solution. Specifically, the value of n will always be between 1 and 1000, inclusive. The output array must contain exactly n integers, all of which must be unique, and their sum must strictly equal 0. Now, let's consider some edge cases to understand the problem better. For the smallest input, where n equals 1, the only possible solution is 0, as we discussed earlier. For a larger input, like n equals 1000, the solution must efficiently generate 1000 unique integers while ensuring their sum is 0. This requires careful construction to meet the constraints without wasting computational resources. Finally, the parity of n, whether it's odd or even, can influence the solution. For odd values of n, the array must include the number 0 to balance the sum. For even values of n, the array must balance positive and negative integers without including 0. Meeting these requirements is key to solving the problem efficiently and correctly. To begin with, let's consider the brute force approach. The intuition here is straightforward. We generate all possible subsets of n unique integers and check which of these subsets sum up to 0. For example, if we select integers from a range like n to n, we could generate combinations and evaluate their sums. While this approach may sound viable, it's highly inefficient. Generating all subsets has an exponential time complexity of 2 to the power of n, which means even moderately large values of n would result in impractical computation times. Additionally, the space complexity of n for storing subsets further adds to its limitations. For these reasons, this approach is rejected, as it fails to scale efficiently for larger inputs. Now let's explore a much more efficient and optimized approach, constructing symmetrical pairs. The idea here is to take advantage of the symmetry between positive and negative integers. For any positive integer x, its negative counterpart x cancels it out, ensuring a sum of 0. We can use this property to construct an array of size n by pairing integers symmetrically around 0. The steps are quite simple. We start by initializing an empty array. Then, for values of I from 1 to n//2, we add both I and I to the array. If n happens to be odd, we include 0 to balance the sum. This guarantees that all integers are unique and their sum equals 0. For even n, every number is paired symmetrically, and for odd n, the inclusion of 0 ensures balance. With a time complexity of n for constructing the array and a space complexity of n to store the result, this approach is both efficient and straightforward. This approach was chosen because of its simplicity, efficiency, and deterministic nature. It satisfies the problem's constraints of uniqueness and a sum of zero with minimal computation. Now, while there is an alternative method involving arithmetic progression, it is slightly more complex. In this method, we create an array of n integers summing to 0 by centering an arithmetic progression around 0. For example, if n is 5, the array could be -2, -1, 0, 1, 2. The logic works because the sum of such a progression is always 0. The steps involve computing the sequence symmetrically and adjusting it for even values of n by excluding 0. While this approach also has a time and space complexity of O(n), the construction process is less intuitive compared to the symmetry-based method. Ultimately, the symmetry-based approach was chosen for its clarity and practicality. It's simple to implement, easy to understand, and guarantees a valid result without requiring any additional adjustments or complexity. The arithmetic progression method, while equally efficient, introduces unnecessary difficulty in constructing the sequence, which makes it less approachable, especially for beginners. On the other hand, the brute force approach, as discussed earlier, is computationally infeasible for larger values of n due to its exponential complexity. By directly leveraging the symmetry of integers, the chosen strategy offers an optimal balance of efficiency and simplicity, making it the most practical solution for this problem. In this problem, the goal is to find all subsets of integers within a given range such that the sum of elements in each subset equals 0. To achieve this, the algorithm begins by understanding the input and output. The input consists of a single integer, n, which defines the range of integers from n to n. The output is a list of subsets where the sum of the integers in each subset equals 0. The first step in the algorithm is to generate all subsets of integers within the range n. To do this, we use the power set approach, which involves iterating through all possible combinations of the integers in the range. For a range of size 2n plus 1, the total number of possible subsets is 2n plus 1. By representing these subsets using a bit mask, we can efficiently encode whether each element is included or excluded. For instance, if n equals 2, the range is -2, -1, 0, 1, 2, and each subset corresponds to a binary number, such as 00000 for no elements and 111114 for all elements. After generating all subsets, the algorithm filters them by calculating the sum of elements in each subset and retaining only those where the sum equals 0. Once all subsets are generated and filtered, the algorithm proceeds to return the final result, which is a list of subsets where the sum of the elements equals 0. However, there are key insights to keep in mind about this approach. First, generating all subsets is computationally expensive due to the exponential growth in the number of subsets as the size of the range increases. This means that for large values of n, the algorithm becomes infeasible. Second, using a bitmask representation to generate subsets helps optimize the process by efficiently encoding the inclusion or exclusion of elements. Finally, we must handle edge cases. When n is 0, the range contains only 0, and the only valid subset is 0. For n less than 0, the range is invalid, and the algorithm should return an empty list. These considerations ensure that the algorithm is robust and handles special cases appropriately. To implement this algorithm, we rely on a few key data structures. First, the input range from n to n is stored in a list, which allows for straightforward iteration and easy generation of subsets. Next, subsets are represented as a list of lists during computation. Each subset is stored as a list of integers, and all subsets are collected into a larger list. Finally, we use a separate list to store the subsets that meet the condition of having a sum of 0. These data structures are simple yet effective, enabling us to efficiently generate, process, and store the subsets that satisfy the problem's requirements. Analyzing the complexity of this algorithm reveals the trade-offs involved in generating all subsets. The time complexity is dominated by the process of generating all subsets, which requires 2n plus 1 operations, as there are 2n plus 1 possible subsets. Additionally, calculating the sum for each subset involves iterating through its elements, which takes k time on average, where k is the average size of a subset. Therefore, the total time complexity is k*2n plus 1. The space complexity is primarily determined by storing all subsets, which requires O(2) plus 1 k space, where each subset contributes k elements on average. The result list also contributes to the space complexity, as it depends on the number of subsets with a sum of 0. This analysis highlights the exponential nature of the algorithm, making it suitable only for small input sizes. To better understand the algorithm, let's walk through an example where n equals 2. The range of integers is -2, -1, 0, 1, 2, and the total number of subsets is 2⁵ equals 32. Each subset corresponds to a binary representation, where each bit indicates whether an element is included or excluded. For example, the binary string 00011 represents the subset -2, -1, while 11100 corresponds to 0, 1, 2. After generating these subsets, we filter them by calculating the sum of their elements. Only subsets with a sum of 0 are retained. For this input, the valid subsets include -2, -1, 1, 2, -2, 2, 0. These subsets make up the final output of the algorithm. This example demonstrates how the algorithm systematically generates, processes, and filters subsets to solve the problem. The provided Python solution generates a list of n unique integers that sum up to 0. The function sum0 takes an integer n as input and returns the resulting list. Here's how the code works. 1. Initialization. An empty list result is initialized to store the integers. 2. Generate pairs. The for loop iterates over the range from 1 to n/2 plus 1. For each value I, two integers are added to the result list, I, negative of I, and I. This ensures that each pair of integers sums to 0. For example, if n equals 4, the loop adds -1, 1, and -2, 2 to the list. 3. Handle odd n. If n is odd, the sum of the integers added so far will be 0, but the count of integers will be less than n. To address this, the code checks if n%2 equals 1 and appends 0 to the result list. This ensures that the total count of integers becomes n. 4. Return result. The function returns the result list containing n unique integers that sum to 0. ###example walkthrough. For n equals 5, the loop adds -1, 1, and -2, 2 to the list. Since n is odd, 0 is appended, resulting in -1, 1, -2, 2, 0. For n equals 4, the loop adds -1, 1, and -2, 2 to the list. Since n is even, no extra element is added, resulting in -1, 1, -2, 2. This solution is efficient with a time complexity of O(n), as it iterates up to n/2 and performs constant time operations for each iteration. It ensures correctness by always producing n unique integers that sum to 0. This is the Java implementation of LeetCode problem number 1304, find n unique integers sum up to 0. The logic mirrors the Python implementation, using an array to store pairs of integers, I, to ensure their sum is 0. If the input size n is odd, a 0 is added to the array. The solution uses a simple loop and conditional check, making it efficient with O(n) time complexity. Key differences from Python include explicit type declarations, array usage instead of lists, and zero-based indexing for array manipulation. To solve this problem, we start with the example where n equals 3. First, we initialize an empty list called result to store our integers. Next, we calculate how many pairs of integers we need. Since n divided by 2 equals 1, the loop will run from I equals 1 to 1. Here, for I equals 1, we generate a pair of integers, -1 and +1. We append both to the result list, so now result becomes -1, 1. After the loop finishes, we check if n is odd. Since n equals 3, which is indeed odd, we append 0 to the result list. This gives us -1, 1, 0. Finally, we return this list as our output, and we can verify that the integers sum to 0 because -1 plus 1 plus 0 equals 0. Now let's look at the case where n equals 4. Again, we start by initializing result as an empty list. This time, since n divided by 2 equals 2, the loop will run from I equals 1 to 2. For I equals 1, we append the integers -1 and 1 to the list, so result becomes -1, 1. Then, for I equals 2, we append -2 and 2, updating result to -1, 1, -2, 2. After the loop, we check if n is odd. Since n equals 4, which is even, we don't add anything further to the list. Finally, we return the result as -1, 1, -2, 2. The integers in this list also sum to 0 because -1 plus 1 plus -2 plus 2 equals 0. Next, we consider the example where n equals 5. Once again, we start by initializing result as an empty list. Since n divided by 2 equals 2, the loop will run from I equals 1 to 2. For I equals 1, we append the integers -1 and 1, making result equal to -1, 1. Then, for I equals 2, we append -2 and 2, updating result to -1, 1, -2, 2. After the loop, we check if n is odd. Since n equals 5, which is odd, we append 0 to the list, resulting in result being -1, 1, -2, 2, 0. Finally, we return this list, and we can verify that the integers sum to 0 because -1 plus 1 plus -2 plus 2 plus 0 equals 0. The time complexity of this solution is determined by the process of constructing a list of n unique integers that sum to 0. First, let's analyze the loop execution. The for loop iterates from 1 to n/2 plus 1, which means it executes n/2 times. Within each iteration, two integers are appended to the list, I and I. Since each append operation takes constant time, or O1, the total time spent in the loop is n/2 *2*O1, which simplifies to O(n). Additionally, if n is odd, a single append operation is performed to add 0 to the list. This is a constant time operation with a complexity of O1. When we combine all these steps, the loop dominates the time complexity, and the overall result is O(n). The space complexity of this solution is primarily determined by the memory required to store the output list, result. Since the list contains exactly n integers, where each integer takes constant space, the total space for the list is O(n). Additionally, no significant auxiliary space is used outside of the result list. The operations performed, such as appending integers and iterating through the loop, do not require any extra memory. As a result, the overall space complexity of the solution is also O(n). When comparing this approach to a brute force method, it becomes clear why the current solution is optimal. A brute force approach might involve generating random unique integers until their sum equals 0 or iterating through all possible combinations of integers. These methods are highly inefficient. For example, generating all unique combinations or repeatedly adjusting numbers could take exponential time, such as O(2 to the power of n, or worse, depending on the implementation. Additionally, the memory required to store combinations or intermediate values in a brute force method could also grow exponentially, leading to a space complexity of O(2 to the power of n. In contrast, the current solution avoids these inefficiencies by systematically generating integers that inherently cancel each other out, achieving the desired result in O(n) time and space. This makes it both optimal and elegant. To formally prove the big O complexity, let's revisit the key operations. For time complexity, the loop runs n/2 times, and each iteration involves two O(1) operations for appending integers. This leads to a total of O(n) operations. If n is odd, adding a single element outside the loop is a constant time operation and does not affect the asymptotic complexity. Therefore, the overall time complexity is O(n). For space complexity, the only significant memory usage comes from the result list, which directly scales with n. Since the list contains n integers and no additional memory is required elsewhere, the space complexity is O(n). Finally, the best, average, and worst cases all result in the same complexity for this problem, as the number of operations is solely determined by the input size n. Thus, the time and space complexities remain O(n) in all scenarios. When solving problems that require finding subsets summing to 0, there are several common mistakes to be aware of. First, overlooking edge cases can lead to incorrect solutions. For example, if the input array contains only positive or only negative numbers, it's impossible to find subsets that sum to 0. Similarly, failing to account for the empty subset as a valid solution can result in missed cases. These issues must be explicitly handled to ensure your solution is both correct and complete. Another common mistake is relying on brute force to generate all possible subsets without filtering out irrelevant combinations. This approach leads to exponential time complexity and is highly inefficient for larger inputs. It's important to prune unnecessary computations early on. Additionally, errors can occur during the zero-sum check itself. For instance, using floating-point operations instead of integer arithmetic may introduce precision errors, causing inconsistent results. Lastly, improper use of hashing is a frequent pitfall. For example, assuming duplicate keys are allowed in a hash table can overwrite values and lead to missed solutions. To avoid this, hashing must be carefully implemented to maintain correctness throughout the process. Another issue to watch for is failing to optimize space usage. Explicitly storing all subsets in memory can cause problems like memory overflow, especially with large input sizes. To address this, it's crucial to develop space-efficient algorithms capable of handling such scenarios. Now, let's focus on key insights for interviews. Problems involving zero-sum often rely on symmetry, such as the relationship a plus b equals 0, which implies a equals b. Recognizing these patterns is critical. Hashing techniques like prefix sums or two-pointer strategies frequently appear in these types of problems, so being familiar with them is advantageous. When it comes to optimization, it's often best to start with a straightforward brute force approach and then refine it. For example, you might reduce time complexity by leveraging hashing, sorting, or mathematical properties. During interviews, make sure to clearly explain the trade-offs in your approach, such as time versus space complexity. Communication is essential. Discuss your thought process, including how you handle edge cases and why you choose specific methods. If you encounter difficulties, it's always a good idea to propose alternative approaches, such as dynamic programming or divide and conquer techniques, to demonstrate your problem-solving flexibility. There are several related problems that can help you build a deeper understanding of zero-sum techniques. For instance, the two-sum problem, LeetCode 1, involves finding two numbers that add up to a target value. Similarly, three-sum, LeetCode 15, asks you to find all unique triplets that sum to 0. Subarray sum equals k, LeetCode 560, focuses on counting the number of subarrays with a given sum, while for sum, LeetCode 18, extends the concept to finding quadruplets. Each of these problems builds upon the principles we've discussed, making them excellent practice. Now, let's explore some alternative approaches to solving zero-sum problems. One efficient method is sorting combined with a two-pointer technique. By sorting the array, you can systematically search for combinations that sum to 0 using two pointers. This reduces the time complexity to O, n squared, for problems like three-sum, though the sorting step adds O, n log n. Another approach is using a hash map to check for complements. This allows you to find zero-sum pairs in constant time, significantly improving efficiency. However, it does increase space complexity, so you'll need to weigh the trade-offs carefully. Dynamic programming is another powerful approach for finding subsets with a target sum. It works well when the target sum is bounded, allowing you to build solutions incrementally. However, for unbounded cases, dynamic programming may not scale efficiently due to its space and time requirements. Alternatively, backtracking provides a flexible way to generate subsets recursively. By pruning paths that exceed the target sum early, you can reduce unnecessary computations. While this approach is highly effective for avoiding redundant calculations, it comes with the drawback of higher implementation complexity. Both dynamic programming and backtracking are advanced techniques that can be particularly useful in challenging zero-sum problems, so understanding when and how to apply them is crucial for optimizing your solution. Great job following through this problem. We reviewed an elegant solution to construct an array of integers summing to 0. Remember, mathematical intuition and simplicity are key takeaways here. Thanks for watching, see you in the next video. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!